Hi, this unit is going to be on vector quantized variational autoencoders. And I'm going to start just by showing some results. We've seen a little bit of this before, but I want to go over it again. So this is Gaussian VAEs when they were sort of first introduced in 2013. So the idea here is we're sampling images from the distribution on images that have been learned by the VAE. And to review sort of how to think about this, the autoencoder is taking an image, it's mapping that image to some latent representation. And then in these images, what it's doing is it's taking the probability distribution it's learned over the latent representation, and it's generating random samples from that and then converting them back into the image. So think in terms of ordinary image compression. You take an image, you produce a compressed file, that's your latent variable in the framework we've been working with. Then you, if that's perfectly compressed, it's kind of noise. It can't be compressed further. So I should be able to take a random sample from it and generate an image. And if everything's been done really well, a random sample from the compression should generate a random image from the distribution over images. So it should generate a natural image. So these images don't look great. This is 2013. And from a long time, from like 2013 to let's say 2018, GANs were able to generate much more compelling images. But GANs have this issue that you're not sure if it's really covering the space of images. There's no good quantitative measure of the performance of a GAN. So for that reason, I've always been much more sympathetic to the VAE approach to image modeling. And that's related to the fact that in language, straight up language modeling, straight up use of the cross entropy loss has proved extremely effective in modeling language. Okay, so these are images generated from random compressions in 2013. Bang, 2019. This is a variational autoencoder. It's trained by autoencoding. These are sampled faces from the implicit distribution of the model. So you generate a random compressed image, latent image Z, and then you convert that back into an image. And this is trained on Celeb. This is class conditional image representation. So we represent images on dogs and butterflies and birds. And there's a different model for dogs, butterflies, and birds. And this shows the difference. I think these images, which are very striking to me, you know, this dog doesn't exist, this butterfly doesn't have a head. What's the difference here is that the background has been completely blurred or just smoothed out. And that shows a real difference between what's happening here and what's happening with a GAN. A GAN would have no trouble, a discriminator would have no trouble recognizing that the background's been smoothed out. So we're doing something else here. We're not using the discriminator. We're just looking at, you know, how many bits does it take to represent the image, or trying to model the probability distribution over images in terms of latent variables. So it's different. And the fact that it's working this well suggests that, you know, we should be continuing to push both of these lines, GANs and autoencoders. How does a vector quantized autoencoder work? So basically, it's performing k-means on vectors in higher layers in a convolutional neural network. And because I'm going to use X and Y for spatial coordinates, I've been using Y for the observation, the image or the sound wave. But now I'm going to use S for the image or signal and X and Y for spatial coordinates, just notational convention. So let's do this more explicitly. So the variational, the vector quantized autoencoder is going to take an image. It's going to pump it through a convolutional neural network up to get some layer in the convolutional neural network. So this layer in the network has spatial dimensions, and it also has neuron dimensions. It's a standard CNN. And if you remember when we first started talking about rate distortion autoencoders, image compression, right? An image compression technique took the image up to some layer of the CNN, and then it rounded all the numbers in here, and that rounding operation made it more compressed. Here we're going to do something else. This layer in the convolutional neural network has spatial dimensions, and at each position it's got a vector, right? A response from all of the neurons at that position forms a vector. And what I'm going to do is I'm going to take those vectors that occur at the individual spatial locations here, and intuitively I'm going to run k-means. And k-means is going to produce k clusters, and for each cluster it's going to have a center vector. And what I'm going to do is I'm going to snap each vector here into its cluster center. And that's going to produce what I'm going to call a symbolic image. So this image has spatial dimensions, and at each position it just has a kind of symbol, which is the index of the cluster center. So I'm going to call this a symbolic image. It's an image such that each spatial location I have a symbol, an index of the cluster. And naively, I mean, this is you can really think of this as an image compression method, right? Naively, I can now represent this with log 2 k bits at each position, right? All I have to do is name which of the k. So that's going to take log 2 k bits, and they use 512, I think, for k. So you can think of this as very much like that image compression algorithm we did a few units ago. But then they do something else, right? So this is going to give you train this as an autoencoder, and that's going to train this code table. Once this k-means code table is trained, we've got k vectors in this code table, which are the centers of k clusters. Once this thing is trained, I can take an image and convert it to a symbolic image, right? A cluster center at each position at some higher at some smaller spatial dimensions than the original image. Once I've done that, I can train an autoregressive model over the space of symbolic images. So the autoregressive model is going to predict one symbol at a time from the other symbols. This is called a pixel CNN. And it's autoregressive, which means I can both calculate the probability of a given symbolic image, and I can sample. Symbolic images by just going along autoregressively and sampling from the conditional probability on the next symbol. It's just like a language model. This symbolic image is just like a list of symbols now, and we're just doing an autoregressive model of this. There's a lot of subtlety in exactly how you want to predict the next, or which pixel you want to predict next, and what you want to look at when you predict that pixel. But the point is, it's autoregressive, right? We're predicting one symbol at a pixel at a time. And that's going to turn out to give us a powerful way of modeling the probability distribution over images. And then instead of saying, well, we're going to spend log 2 k bits per symbol in this image, no, we're just going to take the whole probability of this whole thing under this autoregressive model and take the average number of bits per pixel, log 2 of that probability divided by the number of pixels, just like a language model. So this is a kind of language modeling of the symbolic images. Then what we do is the autoregressive thing is something we can sample from. So we sample from this autoregressive distribution and decode it into an image. And that's when we get these really striking images. I'm being a little sloppy here. This is a one-layer model, and I'm going to describe a one-layer model because it's simpler. But those really nice images come from two-layer models. And the two-layer models are sort of roughly analogous to the style GAN, where you have different noise being fed into the system, different distributions over, there's going to be multiple pixel CNNs at different levels feeding into the process of generating the image. And that's how you get the really nice images. Okay. So the first thing I want to do is just, I'm going to be obsessive a little bit, and I'm sort of going to drag you through some details. And to drag you through some details, I'm going to write out the equations explicitly. So it's very simple, right? We have an image. We pass it through an encoder. This is just a convolutional neural network. This is the layer of the network at some point in the convolutional neural network. It has spatial dimensions and neuron dimensions. Then what I'm going to do is I'm going to construct a symbolic image by finding the nearest entry in the code table. I'm going to take an argmin over the symbols of the distance between the vectors for that symbol and the vector that I've constructed at this point in the spatial location. And this is going to be the symbolic image. It's just going to be the K that names the nearest vector in the code table. So this is the symbolic image. Then I can take this symbolic image and decode it just by back into a vector at every position, just by saying the vector at position XY is taken from the code table for the code that's now stored at XY. So it's easy to, you do a nearest neighbor calculation of a code, of a symbol, a cluster at each position, and then you can convert that back into a layer of a neural network by just using the cluster center as the vector at a position. And then you run that through a convolution transpose that can turn that back into an image. We talked about how to generate images by a kind of a convolutional process that increases the spatial resolution. So this is all very simple. The latent variable is this symbolic image that naively only requires XY pointers to symbols. So it's that many bits. Okay, that's the model. The question now is, how do we train it? So this is very much like that image compression algorithm, right? We're going up to some layer in a regular convolutional neural network. Then we're going to a discrete representation, in this case, a k-means-like representation. And then we're coming back from that discrete representation to the image, and then we're going to measure a distortion. And so the training function is now just going to be it's just going to look at the distortion. So before we talked about a rate distortion trade-off, we've got a limitation on the rate now. We've got this limitation on the rate. It's xy log k. So k is limiting the rate. And then the objective function for the training is just going to be the distortion. And the weird thing about the distortion is you're going to look at the distortion at the image plane, right? There's an image, there's an L2 distortion between the original image and the reconstructed image, and that's going to be part of our loss function. And then the other thing that's going to be part of our loss function is the distortion due to the quantization. So this was constructed from the image coming up. This is snapping each vector in here to its center mean, the result of that. And we're going to look at that difference squared. And that's also going to be, that's a distortion that's happening in the network. There's a distortion on the image, and then there's a distortion at this layer in the network where things are being quantized and then coming back. So this distortion in the network can be written this way. This is just this. It's the codebook entry. So this distortion can be written this way. And what we're gonna do is backprop from this distortion loss term into both the codebook and the network generating this image, this layer of the CNN. So we're going to take this loss and backprop it into the network generating this layer of the CNN and into the codebook. So those two things are going to be separated, and the gradients are going to be calculated differently. So when we backpropagate into this, we're just going to take this expression and backpropagate it into here, but we're not going to backpropagate this beta. Here's our original loss function. It has this weight beta on this term. And this weight beta is only going to be applied to one of the gradients. It's a pretty funky thing. So the beta is applied to the gradient back into this layer. And it's not applied to the gradient in here. So it's not a simple natural, or it looks like it's not a simple natural enforcement of this loss function, where there's a beta here. However, these are being applied to different parameters, right? The beta is being applied to this parameter, and there's a loss being applied to this parameter that does not have the beta. And that can be interpreted as just here, just using different learning rates for this parameter than for that parameter. And so what's going to happen is if you have a stationary point and the gradients are all zero, the fact that this gradient is zero is not affected by the value of beta. So this beta is, if you have parameter-specific learning rates, that doesn't change the stationary point, the point where the gradient is zero. So this can be when you write the updates this way, it can be interpreted as parameter-specific learning rates, which are benign. But it is also if you look at the gradient being passed here, this beta is also playing a weighting role between these two terms of the loss function. So this term in the loss function is also going to be back propagated into this. So beta is also influencing the relative weight of these two terms when you're doing the back propagation into this network. There's this thing in PyTorch called Detach. You can detach part of your parameters from a loss function. So the way this gets implemented is that this piece is detached from this gradient, and this piece gets detached from this gradient. There was a discussion at office hours once about what detach is used for, and this is a place detach is used. It's kind of funky, but I still think it is sensible. So the relationship to k-means. So the only thing that's updating, this code book is this gradient here. And this gradient here, if you imagine, again, think of a stationary point of this update process. Since this is saying that the only loss that's being applied to the code book is the squared difference loss. That's the only loss being applied to the code book. And what that means is that at a stationary point, the code book is in fact a stationary point of the k-means update algorithm for the space of vectors being observed in this layer of the images. So it really is very close to k-means. I'm really dragging you through this. We have another problem, which is the problem we had in the earlier image compression algorithms, is that when you snap to a discrete representation, the gradients are zero. So so how do you pass the gradient back? If we look at our loss function, there's a gradient coming back from the image distortion. And that gradient coming back from the image distortion comes back to this tensor. So this tensor is going to have a gradient because it is the thing that generated the image, the S hat. So it's getting a gradient from this other term. And that gradient from that other term has to go back into the encoder. But the encoder has this quantization step in it that is not differentiable. So there's something called straight through gradient. You take the gradient being computed for the tensor after it's been snapped, and you simply assume that gradient can be used as the gradient for the input tensor before it was snapped. So that's called a straight through gradient. And that sort of assumes that this tensor and these tensors are close, right? So it's assuming that the distortion at this level of the network is small, which is true in these networks. I can't help but wonder about some strange properties of this and make some suggestion. Beta here is playing two roles. It's playing a relative learning rate role here, the relative learning rate of this versus this. It's also influencing the relative weight of this term versus this term for the gradients that get passed back to this, this tensor. So the question is, it's natural to ask whether it would be better to have two hyperparameters for those two functions, the relative weight of the loss terms and the relative adjustment in the learning rates. Okay, this is what's happening in the multi-layer case, right? We have a convolutional neural network that goes up here. Then we do vector quantization at the top layer. Then we take a decoder here to make a prediction about what should be here. We combine these two. We just concatenate these two vectors. And then you do a vector quantization of that. So we've got two layers of vector quantization. And this to me is somewhat, and then you do two pixel CNNs. You develop a probability model of this, and then you develop a probability model of this given this. Because we have these multiple layers that we can get out of this autoencoder. And now we're just training probability models of the different layers. Then when we do sampling, we're generating multiple layers of the discrete images from a probability distribution specific to that layer. And this to me is somewhat reminiscent of the multi-layers in the style GAN. So again, I think both, you know, the VAE and the GAN approach both need to be pushed. There's this weird evaluation they do in VQ-VAE2. What they're going to do is evaluate how good, how well they can generate labeled images just by generating images. So you remember when you do ImageNet, you do class conditional image generation. You generate dogs and butterflies and birds. And that means that you can generate class image pairs, right? You name the class, you generate an image for that class. So I can generate a very large number of class image pairs. Then I can train a classifier using standard classifier training on the synthetic data set of labeled images generated from your model. And then you can test the classifier trained on the synthetic data on real data. And so that's what we're looking at here. So big GAN can be used to generate labeled images. You can train on those images, and then you get these accuracy numbers when you test on real images. The VQ-VAE does significantly better. So it's suggesting that there's something qualitatively better about the images that it's generating, at least for training classifiers. And then they do some statistical tricks to make the generated images have the same statistics as the natural images, and that boosts their performance a little bit. But they're, you know, this goes from 65 to 80, and real data gives 91. So it's a really significant difference relative to the GAN approach. Another thing that you cannot do with GANs is measure, is actually get a measure for a given image of the perplexity, you know, the bits per pixel that your model is demonstrating. So in language modeling, you work really hard, and perplexities in language model have made dramatic improvements over the last 5 years, 3 or 4 years. And that improvement in perplexity seems to be the source of the dramatically improved language evaluation performance. So the ability to train directly on perplexity or log probability, negative log likelihood, that your model is establishing for your data seems like it's important. And that is something you can do you can actually calculate the negative log likelihood that the model is establishing for the image data. Now, this has to be combined with a distortion number for the images, because you're not going to reconstruct a continuous image exactly. But the images we've seen are achieving very, very small distortions. Okay. You can also just do straight up image compression. So I can take an image, an original image. I can generate just the top layer, or I can take that image and compute just the top layer symbolic image and generate from that down, generating the lower images from the probability distribution. So that's going to give me more compression, but more distortion. If I just keep the top image of the encoder, right? Keep the top symbolic image of the encoder. If I keep the top two, it gets better. Higher rate, lower distortion. If I keep the top three in a 3-layer network, I get a higher rate and the lowest distortion. And these distortions, if you keep all 3 layers, the distortion goes essentially to 0. Okay, now we're going to move on to a pre-training section. Thank you.